Okay, so I believe we are recording, and the only way, yes, we are. Okay, cool. Thanks for telling me about that. So, so let us start today then. This is 04/14/21, and let me also start my stopwatch so that I know how long I've babbled on here. So, um, there we go. All right, so everyone's aboard, and what we're going to do is start with these equations and just ask some simple questions. Now that we understand that the population inversion is important and all that, well, let's just say that, so n1 dot is equal to minus n2 dot is equal to the spontaneous emission out from N2 into N1. So therefore that's why it comes in as a positive term, because it adds to the N1 population. And then there is um, the stimulated emission into N1, so that's a positive term, and the absorption out from N1, and that's with a negative sign, right? So the rates are equal for the stimulated absorption and emission. And remember what each of these symbols are. Spontaneous emission, stimulated emission from N2 to N1, absorption from N1 to N2. All right? Okay. And just some simple questions, like let's say that let's solve for the population in N2 in the steady state. Okay. So whenever we say steady state, that means that you set the change 0, right? It's in the steady state, so it can't be changing. And so then that means that, in this equation up here, A21, N2, well, and N2 dot is 0, and so is N1 dot, because remember, N1 plus N2 is a constant. That's the total N. And of course, that means N1 dot plus N2 dot is 0. So this is 0, that means N1 dot is also 0, obviously. But anyway, so this means that the sum here, okay, and these are now the steady state values, is equal to 0. Yeah? So, and of course, N1 plus N2 is a constant N, and this, of course, also means N1 steady state plus N2 steady state is N, right? And so I can substitute for N1 steady state, simply it's that, okay? And so from here, therefore, I can solve, I get an equation for just N2 steady state, okay? And so I can solve for N2 steady state. It's because there's one term with N and the other terms have N2 steady state in them. So I just collect the terms together, and N, the term going as N, which does not have an N2 steady state in it, that you take over to the other side, and then the coefficient of N2 steady state everywhere is going to be A21 plus 2 sigma phi, right? Because this minus N2 steady state, well, there was a minus sign, so this becomes twice N2 steady state, okay? And therefore you get this. So you can see that that's what you're going to get from here, okay? So right away, you can see that, you might say that, well, if the goal is to create a population inversion, to pump up N2, right? Increase N2 as much as possible. And of course, the way to do that is to just start increasing the illumination to try and get as many atoms up from 1 to 2. And we've discussed this before, that obviously this then, but they also get stimulated back at the same rate. So you really can't win. And we will see that categorically in this case. So what you do is you say, okay, I'm just going to take my phi and take it up, right? So the best you can do is that as the incident photon flux goes to infinity, you can see that N2 steady state is, so as it goes to infinity, so the term on the top stays. On the bottom, you can neglect the A21, and you have this. And of course, as we were predicting, this turns out to be N over 2, right? And this implies that N1 steady state is N over 2. And so your population inversion, the best you can do, population inversion maximum, the best you can do is 0. Okay? So it's either negative or 0. It's never positive. So for this reason, you can never make a laser from a two-level atom model. So I just can't do it. Okay? Okay, so that was one point that I wanted to make here. The other thing is that one other thing we get from here. So this is one important point.
Professor.
Yeah.
Why can you just get rid of A21 there?
Because I made the in an effort to create a positive population inversion, I put in the incident photon flux that pumps the atom up from level 1 to level 2. I made it as large as I can. And so if this goes to infinity, then you notice that in the denominator, I can throw away this term compared to that.
Well, why can you do that?
Oh, because, well, the spontaneous emission rate is a constant. I mean, that's just, you know, spontaneous emission does not depend on how hard I pump the atom. It just says that if the atom is in the excited state, then the atom will spend on an average 16 nanoseconds in the case of rubidium, and it's just going to jump back down. So it's a fixed rate. The spontaneous emission rate for rubidium, for example, is 6 megahertz, and it's fixed. Like,
why can you assume the flux is infinity?
Say that again?
Why can you assume the flux is infinity?
Oh, no, that is me trying to increase the population in level 2 as much as possible by providing the incident photon flux.
So that's just saying, in the case of max,
yes.
When you get as much as possible,
yes,
then you treat it as very large.
Exactly. Yeah. So as we try to, you know, so this is our goal here. So as we try to pump the atom as, okay, sure, as hard as possible. Does that make sense? Is that good? Okay. So, but that's a good question, what you just asked, because that is my big second point, that this actually tells me a criteria for what is, this establishes, this is very important, this establishes a criterion, because if you remember, I was saying, you know, last time I was saying we were going to talk about very important things such as strong excitation versus weak excitation. We've already talked about population inversion, but I was going to talk about saturation intensity. And so we've already discussed rate equations. But this guy and this guy, these are very important concepts, and we'll talk about that right now. That this establishes a criterion for strong versus weak excitation. Okay, because this tells me that strong excitation means that your 2 sigma phi is, the criterion is established by comparing 2 sigma phi versus the A21. Okay, and so just remember that this is your excitation or pump rate. This is the spontaneous emission. Okay, and so when we say excitation, this means it's the stimulated emission and absorption. So this tells me a criteria where if this is much greater than that, that's strong excitation. If it's much weaker than the spontaneous emission rate, it's weak excitation. All right, and this is kind of neat that the place where they're equal, is where you will notice that, and by the way, this is a 2 times sigma phi, so I should be careful. The excitation rate, so that is 2 times the stimulated or absorption rate. Okay, and so when twice your stimulated emission rate is equal to the spontaneous emission rate, so what is that intensity? I mean, the intensity. So here's the definition of the saturation intensity, and it's an interesting quantity. Saturation intensity. Okay, the saturation intensity is the value of the excitation intensity given by phi. The value of the excitation intensity at which the stimulated emission, at which the spontaneous emission rate. Now the spontaneous emission rate has nothing to do with the excitation intensity. It is a constant for the atom, right? It's 6 megahertz for rubidium. It's 10 megahertz for sodium. You've derived these, you've calculated these quantities. It's the excitation intensity at which the spontaneous emission rate equals twice the stimulated emission rate. The stimulated emission rate very much depends upon the intensity, right? Just by the nature, the definition of stimulated emission, remember? It happens only when another photon happens to be in the vicinity of an excited atom. So, of course, it depends upon the excitation intensity. Twice the stimulated emission rate. Okay? And now this is the value of the excitation intensity. So what is that value? Okay. So I should write, and that value is equal to, it's defined as I sat, and it's equal to the the value at which these two, let me call that value of the photon flux equal to phi sat. So this is equal to phi saturation multiplied by the energy per photon, because remember, this is the number of photons. It's a flux, right? I mean, we looked at the, what was the flux again? Here it is. So remember, we defined the flux as intensity per photon energy. So I need to multiply this by the photon energy, so that would be h nu. Okay, so that's the value of the saturation intensity. Okay, and as an example, I do know what it is for rubidium. I actually do not know it off the top of my head for anything else, but it is for rubidium. It's 1.64 milliwatt per square centimeter. Roughly speaking, it is the intensity at which the word saturation, so the precise meaning of why it's called saturation intensity is given by this equation, because that's where you at that value, what happens is that what happens to the the steady state. First of all, I mean, it's called the saturation intensity. Why? Because roughly speaking, in your mind, you can imagine an atom being excited to the excited state and falling back to the ground state, excited to the excited state, falling back to the ground state. Now, every time it goes up to the excited state, let's say it can spontaneously emit, and so it comes back to the ground state, but now you don't want it to wait. You don't want it to wait too long for another photon to come by so that it can absorb and go back up. So every time it emits and falls back to the ground state due to a spontaneous emission, there should be another photon ready and waiting for it to absorb. And that's, of course, given by this equation to within a factor 2. So it's the excitation intensity at which the spontaneous and stimulated emission rates are equal. Well, to within a factor 2. Okay? And the factor 2 comes from this precise formulation that we just did here. Okay? And you will notice that when the two rates are equal, if you go back to this equation, so if you replace the spontaneous emission rate by the 2 sigma phi, so what you get is that this becomes a n over 4. Okay? So at the saturation intensity, the steady state populations are distributed as 1/4 in the excited state and 3/4 in the ground state. But I mean, that's just a detail. The point is that, when everyone talks about a saturation intensity, in their mind, they roughly have the idea that, yeah, at that intensity, the stimulated emission rate happens to equal the spontaneous emission rate within a factor 2. So, I mean, the factor 2 comes from the math, but the visualization in your head, the reason it's called saturation intensity is because of that. Okay? So, I would like to, this is all I wanted to say about the two-level atom. And so let me pause the recording, let everyone take like a few-minute break here, ask me anything if they want, or wander off for some drink or something. But let's start up again in 5 minutes. Okay, I'm actually going to go over and get some cranberry juice for myself. You see my glass is empty and I want some. So I'm going to go do that, and I'll be back in just a moment. All right, so I'm going to stop the recording first.